Problem 7. A 50-kilogram child stands at the rim of a merry-go-round of radius something, rotating with some angular speed. So what's the child's centripetal acceleration? Well, centripetal acceleration is v squared over r, or r omega squared over r equals r omega squared. And that's the form that will give you the answer for part A because of the information you're given. Oops, part B. So what's the minimum force between her feet and the floor of the carousel or merry-go-round that's required to keep her in the circular path? So let's think about what's happening in part B. The child is spinning around in a horizontal circle, and there must be a force, a centripetal force, pointing toward the center of the circle to keep her moving in this circular path. That centripetal force in this case is supplied by the friction between her feet and the ground. And that centripetal force from friction, all right, S for static friction, by Newton's second law must equal m times her acceleration. That's Newton's second law in the radial direction. And since we found AC, we can just plug in and figure out how big that force must be. So part C, well, how sticky does the floor have to be to provide that much force? What's the minimum coefficient of static friction that's required? Well, again, this motion is happening in the horizontal plane, so the static friction force equals mu times the normal force on the child, which, because all this is horizontal, we've done this problem a million times, the normal force is mg, the child's weight. So you can solve this for mu s. And the way the numbers in this problem work out, the value you find for mu s is unrealistically large. Like it's maybe around 2. And that's an enormous amount of static friction. That essentially never happens. You'd be strapping your feet to the platform. In most situations in daily life, the coefficient of static friction between two surfaces is less than 1. So whatever number you find here, it's unrealistically large. And the fact is that for this speed of merry-go-round, there's not enough friction to hold the child in place. They will slip off, and this turns into the situation we were talking about in the lesson on centrifugal or fictitious forces. The child will continue moving according to Newton's first law, and from their point of view as a rider of this merry-go-round, it sort of feels like there's a fictitious force throwing them off the merry-go-round. There's not really a force throwing them off, it's just their inertia carrying them in a straight line at constant velocity. Because there's not enough friction force to hold them in that circular path.